lithium ion batteries for electrical vehicles. The global motor vehicle industry is rapidly steering away from the internal combustion engine. Electric vehicles are increasingly attractive for their potential to reduce greenhouse gases and decrease dependence on oil. By 2022, more than half of new vehicle sales will likely consist of hybrid electric, plug-in hybrid, and all electric models. For automakers, the key for this huge shift will be lithium ion batteries. While 96% of all hybrid available on the world market today run on the nickel metal hybrid batteries within the 10 years, 70% of hybrids and 100% of plug-in hybrid and all electric vehicles are expected to run on lithium ion. If the United States is to compete in the future auto industry, it will need to be a major player in lithium ion batteries. Today, lithium ion batteries found in nearly all consumer electronics and made almost exclusively in Asia will require additional technology advances before they can be applied widely to tomorrow's electric vehicles. Still, needed are improvements in safety and durability along with the cost reductions. The current cost of lithium ion batteries for electric vehicle applications is 4 to 8 times that of lead acid batteries and 1 to 4 times that of the nickel metal hybrid batteries. Although all the researchers in the different universities contributions to the development of the rechargeable lithium ion batteries, the United States appears a commitment to learning from the past experience in seizing the opportunity to be a leader in lithium ion batteries for electric vehicles. And this video represents the total scenario of lithium ion batteries for hybrid and all electric vehicles and identifies the manufacturing that takes place in the different countries. Lithium ion batteries are projected to become the most popular battery for plug-in and fully battery electric vehicles, while other types of the batteries including lead acid and nickel metal hybrid will continue to retain the considerable market share in the short term. Lithium ion batteries are expected to dominate the market. Compared with the other relevant battery types, lithium ion batteries have the highest power density. The cost is rapidly decreasing. It is important that battery manufacturing takes place near auto manufacturing. Beyond difficulties of the customs, transportation, shipping regulations, and high shipping cost of heavy items, battery and electric vehicle manufacturing are inherently connected due to sharing in R&D and manufacturing facilities. Lithium ion batteries are the most suitable existing technology for electric vehicles because they can output high energy and high power unit of battery mass, allowing them to be lighter and smaller than other rechargeable batteries. These features also explain why lithium ion batteries are already widely used for consumer electronics such as cell phones, laptop computers, digital cameras, video cameras, and portable audio and game players. Other advantages of lithium ion batteries compared to lead acid and nickel metal hydride batteries include high energy efficiency, no memory effects, and relatively long cycle life. Some of the definitions related to the batteries. Anode. The negative electrode typically made with a graphite active material coated on a metal foil current collector, and generally copper material are using here. Cathode, the positive electrode typically made with a metal oxide or a phosphorus olivine coated on a metal for foil current collector, and generally we are using here aluminum. And third component is the electrolyte, lithium salt in a mixture of flammable organic carbonate solvents. Another component cell, a single battery pack, an assembly of cells that are connected in series and are parallel. Each battery pack contains only one type of cell. Connecting cells in parallel increase the pack capacity ampere hour, and in series with the pack voltage, that is, and y times 3.6 volts, whereas x and y are the number of cells that are connected. And another definition is primary lithium metal cells, and another one represented here is the non rechargeable lithium metal cells. These cells have lithium metal anodes paired with a variety of cathode materials and corresponding nominal voltages 1.5 volts to 3.5 volts. Depending on the chemistry and application, cells may be available in button and cylindrical form factors. These cells are not rechargeable. And coming to the secondary recharge or rechargeable lithium ion cells, these cells are rechargeable depending on the quantity, quality, design, and operating window. These cells typically can be cycled from hundreds to thousands of cycles. The long cycle life is made possible because the lithium is not present in metallic form. Lithium is intercalculated into electrode active materials, that is graphite and lithium metal oxide, and moves from the anode to the cathode during discharge, and from cathode to the anode when charging in ionic form. Lithium ion cells are generally available in cylindrical, prismatic, and pouch form factors. Coming to the lithium ion, a lithium ion battery is a type of rechargeable battery in which lithium ions moves from negative electrode to the positive electrode during discharge and back when charging. Next one, lithium ion polymer cells. Same chemistry as lithium ion cells, but the electrolyte is made as a gel with a polymer host which reduces flammability and prevents leakage of liquid electrolyte from a damaged cell. Coming to the pouch cell, the case of the battery is a polymer aluminum laminate similar to the material used for potato chip bags, allowing for light and slender design. And another definition is C rating, a dimensionless way of expressing discharge and charge rates which allows the rate capabilities of different cell designs and chemistries to be compared. Cells designed for high energy may have continuous discharge rates with plus rates up to the 5C. And another definition is battery capacity ampere hour, the rated coulombic capacity of the cell. The units of the ampere hour multiplied by 1000 per milliampere hour. The rated capacity is measured at a specified discharge rate, typically 0.2 C or 0.3 C. The actual capacity obtained in use will depend on temperature, discharge rate, and battery state of health, calendar and cycle life, discharge and charge duty cycle and conditions. Coming to the another definition, OCV, open circuit voltage. The open circuit voltage of a cell is present when the current flow is zero and the internal cell state is at equilibrium. For LiMO2 cathode based cell chemistries, the OCV can be correlated with the cell state of charge. The cathode chemistry is the primary factor influencing the shape of the curve, voltage range, and temperature dependence. Iron phosphate cathode material such as a flat curve versus SOC similar to the nickel cadmium and nickel metal hybrid cell types. And another definition is the DOD, depth of discharge window. DOD is defined as 1 SOC. A cell can be discharged 100%, but practically the maximum SOC may be reduced to 95 to 90%, and the minimum SOC may be limited to 5% to 10% to increase cycle life of battery packs. The DOD window may be 80 to 90%. Coming to the another definition, voltage. During discharge or charge, resistances within the cell lower or raise the OCV. During discharge or charge, the resistive losses and chemical energy of the cell will determine the temperature rise or fall in the cell. On discharge, the minimum voltage may be set to 2.75 volt to 3 volts. If a cell is severely over discharged, voltage less than 2.5 volts, the copper subtract of the anode may be dissolved. On charging, the copper in solution may plate out at the cathode forming a bridge or short back to the anode. If the cell is severely over discharged, the resulting short can cause the cell to go into the thermal runaway. The charge voltage should not exceed the maximum rated voltage, typically 4.2 volts. Otherwise, overcharging the cell will damage the cell and positively force the cell into the thermal runaway. And another important definition related to the batteries, watt hour, a measure of energy. The cell will have a rated energy. The actual energy obtained from the cell will depend on the rate of discharge and the temperature of the cell. As rate increases, the cell temperature is lowered, the amount of energy obtained will decrease. Coming to the another one is the battery management system, BMS. Battery management systems are critical to the safe operation of the lithium ion battery packs. The system protects against overcharge, over discharge, and excessive currents and temperatures. The battery management system protects the pack from exceeding upper and lower voltage and temperature limits. It will also limit current as a function of temperature. The charging rates are typically reduced below 0 degrees centigrade and not allowed between 20 degrees centigrade. The battery management system also estimates the pack SOC and available lower and communicates this to the device controller. The battery management system may also be responsible for providing cell balancing. If the device controller or human operator does not respond to the battery management system request to the lower power or stop operation, the BMS should disconnect the path by opening the connector contactor or relay to the pack or blowing an inline fuse. The battery management systems can have multiple configurations depending on applications. That is, central control board with sense leads to each cell or central master board with distributed boards with electronics for monitoring the multiple cells.
Lithium ion battery C rating. The C rating is the tested value at which a battery can be continuously charged or discharged without damage. And this formula allows calculating the maximum constant discharge current you can draw from lithium ion pack safely without harming the battery pack. Maximum current draw equal to the product of capacity ampere hour C rating. For example, if you have 1000 milliampere hour, your safe maximum current drawn would be 1 ampere hour multiplied with 20 coulomb, that equal to 20 amperes. For this particular example, it is possible to draw more current than the 20 ampere, but it is not recommended as it might damage the battery. And coming to the cell energy example, the formula to calculate the cell energy is energy WH equal to the product of capacity AH into voltage V, where Q is the capacity of the battery ampere hour and V is the nominal voltage of the battery V. Coming to the safety aspects of lithium ion batteries. Although lithium ion battery is rapidly adopted safety concern, both fire and explosion hazards, the threatening widespread adoption, battery safety can be broadly classified into three categories. First one, cell design depending on selected materials and circuitry. Second one, use of product in scenarios unexpected by the supplier. Third one, accidents coming from normal recommended operating conditions possible due to the thermal runaway. So coming to the cell design depending on selected materials and circuitry, manufacturers are attempting to produce safer products. There might be an electric protection circuit. In the use of product scenarios unexpected by the supplier, fire and explosion hazards of the lithium ion batteries in phones or electric cars in crowded space should be carefully watched. For example, the thermal behavior of cellular phone models which have been complained to be too hot should be studied experimentally. Both smartphones and tablet computers might catch fires accidentally and even explode by themselves. The consequence can be very hazardous in crowded areas, allowing phone charging. The third safety aspect is accidents coming from normal recommended operating conditions. possibly due to thermal runaway. Very limited uh, explanation is available in the on the explaining thermal runaway. The thermal runaway can be situation when a cell undergoes spontaneous self-destruction under normal operating conditions with two events occurring in the sequence. First one, high power generation to result in high temperature hotspots. Second one, triggering of the propagation of negative electrode by such local hotspots to increase the temperature of the entire cell, giving further chemical reactions or even combination. Flammable gases released would pose fire and explosion hazards for the components housing the cells. However, there is a little available information characterizing the flammability properties of the gases released after cell thermal runaway. Explosion characteristics such as lower flammability limit, laminar flame speed, and maximum overpressure have to be explained by physical principles such as in this particular case. In order to investigate the thermal failure propagation behavior of lithium ion batteries, full scale burning tests have to be conducted. Theoretical physical principles have to be worked out on promoting fire safety design of large lithium ion battery energy storage equipment. And for this type of these conditions, what are the suggestions here? It is not due to the current flow in the battery, it is due to the high voltage and the current it draws from the battery that must go through the battery connection and the inner layer possible voltage gradient due to the difference in the voltage caused by the atomic orbit from non-perfect 2D structure of the total n parallel 2D lithium unit cell grouped into separated cross sections and the number of n layers. Both of these problems can be eliminated if the material separating the layers and the connections terminals are superconducting, as the superconducting separation between the layers will equalize the voltage of all the layers and will remove the connection heating as well. High critical temperature ceramics in its normal phase is a whole conductor and a current is drawn, the lithium ion battery will lose its voltage as well as generate heat in the ceramic. When the current is passing through the metal wire connected to the high critical temperature superconductor, where the charge carriers are holes due to an applied voltage, say from connecting a lithium ion battery, it does not lose energy and due to also the effective mass difference. The electrons in the metal wire can fill the high critical temperature holes. In fact, due to the momentum conservation, it can only have elastic scattering and maintains the current continuously, meaning we can prevent a quick sudden heating as lithium ion battery is connected to a superconductor instead of a normal conductor as current is drawn. There is a certain minor loss in the energy at the joint. Hopefully, it can be dissipated by thermal conduction. But by a superconductor only works in a temperature but below its critical values. Series and parallel battery configurations. Batteries achieve the desired operating voltage by connecting several cells in series. Each cell adds its voltage potential to desire at the total terminal voltage. Parallel connection attains higher capacity by adding up to the total ampere hour. Some packs may consist a combination of series and parallel connections. Laptop batteries commonly have four 3.6 voltage lithium ion cells in series to achieve a nominal voltage 14.4 volts and two in parallel to boost the capacity from 2400 milliampere hour to and 4800 milliampere hour. Such configuration is called 4s2p, meaning 4 cells in series and 2 in parallel. Insulating foil between the cells prevents the conductive metallic skin from causing an electrical short. Most battery chemistries led themselves to series and parallel connection. It is important to use the same battery type with equal voltage and capacity and never to mix different makes and size. A weaker cell would cause an imbalance. This is especially critical in a series configuration because a battery is only as strong as weakest link in the chain. As an analogy is a chain in which the links represent the cells of a battery connected in series. Comparing a battery with a chain links represent cells in series to increase voltage. Doubling a link denotes a parallel connection to boost current loading. A weak cell may not fail immediately, but it will get exhausted more quickly than the strong ones when on a load. On charge, the low cells fills up before the strong ones because there is less to fill and it remains in overcharge longer than the others. On discharge, the weak cell empties first and gets harmed by the stronger bronze. Cells in multiple packs must be matched, especially when used under heavy loads. Single cell applications. The single cell configuration is the simplest battery pack. The cell does not need matching. The protection circuit on small lithium ion cell can be kept simple. The typical examples are mobile phones and tablets with one 3.6 volts lithium ion cell. Other use of a single cells wall clocks typically use 1.5 alkaline cells, wrist watches and memory backup, most of which are very low power applications. Coming to the series connection, portable equipment needing higher voltage use battery packs with two or more cells connections in series as shown in figure. And this figure shows a battery pack with four 3.6 volts lithium ion cells in series, also known as 4S, to produce 14.4 volts nominal. In comparison, a 6 cell lead acid string with 2 volt per cell will generate 12 volts and 4 alkaline with 1.5 volt per cell will give 6 volts. If you need an odd voltage of say 9.50 volts, connect to 5 lead acid, 8 or nickel cadmium or 3 lithium ion in series. The end battery voltage does not need to be exact as long as it is higher than what the device specifies. A 12 volts supply might work in 9.50 volts. Most battery operates devices can tolerate some of the over voltage. The end of discharge voltage must be respected. However, high voltage batteries keep the conductor size small. Cordless power tools run on 12 volts and 18 volts battery. Some mild hybrid cars run on 48 volts lithium ion. High voltage batteries requires careful cell matching, especially when drawing heavy loads or when operating at cloud temperatures. With multiple cells connected in a string, the possibility of one cell failing in a real and this would cause a failure. To prevent this from happening, a solid state switch in for large packs bypasses the failing cell to allow continuous current flow, albeit at the lower string voltage. Cell matching is a challenge when replacing a faulty cell in an aging pack. A new cell has a higher capacity than the others, causing an imbalance. Welded construction adds to the complexity of the repair, and this why battery packs are commonly replaced as a unit. High voltage batteries in electrical vehicles, in which a full replacement would be prohibitive, divide the pack into the modules, each consisting of a specific number of cells. If one cell fails, only the affected module is replaced. A slight imbalance might occur if new module is fitted with the new cells. Coming to the tapping in a series string, there is a common practice to tap into the series string of a lead acid array to obtain a lower voltage. Heavy duty equipment running on a 24 volts battery bank may need a 12 volt supply for an auxiliary operation, and this voltage is conveniently available at the halfway point. Tapping is not recommended because it creates a cell imbalance as one side of the battery bank is loaded more than the other. Unless the disparity can be corrected by a special charge, the side effect is a shorter battery life. Here is why. When the charging an imbalanced lead acid battery bank will regular charger, the uncharged sections tends to develop sulfation as the cells never receive a full charge. The high voltage section of the battery that does not receive the extra load tends to get overcharged, and this leads a corrosion and loss of water due to gassing. Please note that the charger charging the entire string looks at the average voltage and terminates the charging accordingly. Tapping is also common on lithium ion and nickel based batteries, and the results are similar to the lead acid. Parallel connection of electrical vehicles batteries. If higher currents are needed and larger cells are not available, order do not fit the design constraint. One or more cells can be concentrated in parallel. Most battery chemistries allow parallel configuration with little side effect. This figure illustrates four cells connected in parallel in a P4 arrangement. The nominal voltage of the illustrated pack remains at 3.60 volts, but the capacity ampere hour and run time are increased fourfold. Observe the diagram here, and this diagram with the parallel cells capacity in ampere hour and runtime increases while the voltage stays the same. A cell that develops high resistance or opens is less critical in parallel circuit than a series configuration, but a failing cell will reduce the total load capability. It's like an engine only firing on three cylinders instead of on all four. An electric short on the other hand, is more serious as the faulty cell drains energy from the other cells, causing a fire hazard. Most so called electrical shorts are mild and manifest themselves as a elevated self discharge. A total short can occur through reverse polarization or dendrite growth. A large packs often include a fuse that disconnects the filing cells from parallel circuit, and this figure B illustrates a parallel configuration with one faulty cell. Red color indicates the faulty cell here. A weak cell will not affect the voltage but provide a low runtime due to reduced capacity. A shorted cell could cause excessive heat and become a fire hazard. On larger packs, a fuse prevents high current by isolating the cell. Coming to the series or parallel connection, the figure shows the series parallel configuration enables the design flexibility and achieves the desired voltage and current ratings with a standard cell size. The total power is the sum of voltage times current. A 3.6 nominal voltage cell multiplied with 3400 milliampere hour produces 12.24 Wh. Four 18,650 energy cells of 3400 milliampere hour each can be connected in series and parallel as shown in this figure to get 7.2 nominal voltage and a total 48.96 Wh. A combination with the 8 cells would produce 97.92 Wh, the allowable limit for carry on an aircraft or shipped with class 9 hazards material. The slim cells allows flexible pack design, but a protection circuit is needed. Lithium ion itself well to series or parallel configurations, but the cells need monitoring to stay within voltage and current limits. Integrated circuits ICs for various cell configurations or combinations are available to supervise up to 13 lithium ion cells. Large packs need custom circuits, and this applies to the e-bike batteries, hybrid cars, and the Tesla Model 85 that towers over 7,000 to 18,650 cells to make up the 90 kilowatt hour pack. And here the safety devices in series and parallel. Battery management system BMS. Battery management systems are critical to the safe operation of lithium ion battery packs. The system protects against overcharge, over discharge, and excessive currents and temperatures. The BMS protects the pack from exceeding the upper and lower voltage temperature limits. It will also limit the current as a function of temperature. Charging rates are typically reduced below 0 degrees centigrade and not allowed below 20 degrees centigrade. The BMS also estimates the pack SOC and available power and communicates this to the device controller. The BMS may also be responsible for providing cell balancing. If the device controller or human operator does not respond to the battery management system request to the lower power or stop operation of the BMS should disconnect the pack by opening the contactor or relay to the pack or bowling in a inline fuse. BMS can have multiple configurations depending on the application. That is, central control board with a sense V and T leads to each cell or central master board with distributed boards with electronics for monitoring multiple cells.